chemistry concept of the combined gas law. The combined gas law is a combination of three gas laws we've already been studying. The first is Charles' law. Charles' law looks at volume and temperature and basically says that something that's hot will expand in volume. Okay, that's what Charles' law says. It also combines Lusak's law. Lusak's law says if I have a volume that is fixed, like a glass bottle that is capped, and I increase the temperature in it, well, the hotter it is, the particles move faster. As the particles move faster, the pressure inside goes up. That's Lusak's law. And Boyle's law is a little different. Boyle's law simply says if I reduce the volume, what's the result of my pressure? If I expand the volume, well, if I reduce the volume, there's less room in the container, and the air molecules will hit the walls of the container more frequently, increasing the pressure. So we're going to combine all these three, what's known as combined gas law, and it's kind of basically if you take the top of each one of these formulas, volume and pressure, and put them together. P1 times V1 over top of T1 is going to be equal to P2, second pressure, multiplied against the second volume, and divided by temperature. Okay, so we check that out. We see all three of these now can be combined into one, and this is known as the combined gas law. All right, just a little note here. All temperatures must be expressed in your Kelvin temperature, all right? They must be expressed using this, and Kelvin is going to be your Celsius temperature plus 273. Now, the lowest possible Celsius temperature we can have is negative 273 Celsius. So if I substitute that in there, negative 273 plus 273 gives me a Kelvin temperature of 0 Kelvin. Okay, and Kelvin is not degrees, like degrees Celsius. This is just plain old Kelvins, no degrees Kelvins. Okay, guys, we're going to do a few problems today using the combined gas law. Just remember, all temperatures must be in Kelvin. Okay, let's check it out. A 500 milliliter can of gas is at a pressure of 20 kilopascals. If the can is run over by a garbage truck, oh no, and flattened to a volume of 10 milliliters, what is the pressure in kilopascals, assuming the can does not leak any of its molecules? Okay, so let's check this out. You want to pull out the key information here. I have a 500 milliliters at 20 kPa. Okay, so let's write this down here. Let's write down the givens. Volume 1 is going to be 500 mLs. And the first pressure that volume is at is going to be 20 kPa. Now, you're going to notice that temperature has not been expressed. Okay, we're just going to keep that as an aside there. That's my first volume, pressure, and temperature. Now, the second volume, okay, if the can is run over by a garbage truck and flattened to a volume of 10 mLs. So it went from 500 mLs to 10 mLs. That's really shrunk down a lot. What is the new pressure inside? Assuming the can doesn't leak. So you'll notice here, once again, temperature is not used. Anytime temperature is not used, really what you're going to do is avoid it. You're not even going to put it in the equation. So my combined gas law simply says PV over T is going to be equal to the new PV divided by the temperature. But because temperature is not expressed here, what you're going to do is erase it and not even include it in the problem. Now you do that whenever it is held constant or is not even mentioned. Now I'm going to just pause this for myself. I'm going to erase the temperature that I've scribbled out here, okay? Okay, so we got back here, P1, V1 is going to equal my new pressure and my new volume. And so basically, the first question you have to ask is what law is taking place here? What's going on? Okay, this is a pressure volume. This is going to be a Boyle's law. You know, if we go back to the previous slide here, this is going to be a Boyle's law. Pressure and volume is taking place. We remove temperature. When you remove temperature, you pretty much remove Lusak and also Charles' law as possibilities. Now, we're going to plug our numbers in here. Let's take some time and plug the numbers in. Pressure is 20, and the volume is 500. And I'm going to speed things up. I know I should be writing units. I'm just going to speed it up by not doing that. The new pressure I'm going to is going to be the question mark. What's my new pressure? And the new volume is going to be 10 mLs. Okay, so really what we're looking at over here is multiply these two together, and we have 10,000 is going to equal the pressure 2 times 10 And if we divide both sides by 10, we end up with the pressure of going to be 1,000 kilopascals. All right, and so does that make sense in the scheme of things? My initial pressure was 20, and it went up now, skyrocketed to 1,000 kilopascals. It does make sense because the volume changed just as drastically. The volume went from 500 milliliters down to 10 milliliters. So the volume was reduced drastically, causing a drastic increase in pressure. So what we're seeing here, kind of in our heads, we should be saying the pressure, what's going to happen to it? Well, I don't know. Volume was originally big, and it shrunk down. As you shrink down the volume, the pressure does the opposite. It goes up. So you saw a drastic reduction in volume, leading to a drastic increase in pressure. Okay, guys, let's check out the next problem here. We got a combined gas law problem. If you feel comfortable, why don't you just go ahead and solve it? This will be the last problem that we solve today, actually, on the video. If you feel free to solve it, go for it, okay? One thing I would caution you with, temperature must always be in Kelvin, and this problem does give you the givens in Celsius. A 5-liter air sample at 50 degrees Celsius has a pressure of 107 kilopascals. The temperature is raised to 100 degrees, but the volume also expands to 7 liters. What is the new pressure? Now, this is a good reason why we use the combined gas law, because the 3 individual gas laws are only good under very strict conditions where only like 1 or 2 variables are changing. In this case, I'm looking at changing and varying all of our variables in these gas law equations, so they'll all be needed. Let's start by writing down some information. I start out with a 5-liter air sample. And it is at a temperature, right off the bat, I see negative 50, and also has a pressure of 107 kPa. The first thing I would do then is take my Celsius temperature and add 273 degrees to it. And that's going to give me my Kelvin temperature of 223 kelvins. All right, it must be in kelvins. You're just taking Celsius and adding 273 to it. How about the second set of variables? The temperature is raised to 100 degrees. So I know the temperature is raised to 100 degrees. And the volume expands to 7 liters. What is the new pressure? So what we got here is a couple things going on, actually. Now we're looking at the volume. The volume is expanding. Anytime the volume expands, we would expect the pressure to decrease. Increased volume usually means a decrease in pressure. That's Boyle's law. Pressure and volume. But we're also looking at a little bit like maybe a Lusak's law is taking place here as well. The temperature is increasing from negative 50 to 100 degrees. So the temperature is going up 150 degrees Celsius and only expanding just a little bit. So in this case, the molecules are clearly moving faster, and they could be exerting a greater pressure on the walls of the container. A greater force in the walls of the container, increasing our pressure. So that could be a Lusak's law as well. So the combined gas law is awesome because it takes into account that volume can change, temperature can change, and pressure can change, and handle all these variables changing at once. So let's set up our equation, guys. We start out with a P1 V1 over T1. And it's going to equal our P2, V2, and T2. And one little thing I do realize I forgot was adding 273 to this to bring it up to my new temperature of 373 kelvins. I want to substitute the numbers into these problems here. The pressure is going to be 107. Once again, please forgive me for not writing the units. I'm just trying to save some space on the video slide here. 107 kilopascals is my pressure. The volume is 5 liters. And the first temperature was 223 Kelvin. The new pressure is going to be our question mark, so we're going to leave that. That's what we're solving for. And the new volume is 7 liters. And we have a new temperature of 373. Alright guys, let's go to work on this problem and let's start solving. We're going to be solving for the pressure and using some of our algebra skills. Some students like to cross multiply, some students like to break the problems down to decimal parts. Alright, I'm going to start by doing 107 times 5 divided by 223. And the answer I get when I do that is 2.40. On the other side, I'm now going to be multiplying pressure against 7 divided by 373. And what I end up having is pressure times 0.01, rather 0.0188. Lastly, I need to break this down a little farther and divide each side by 0.0188 and 0.0188. These guys are canceled now. I've isolated my pressure, and 2.40 divided by 0.00188 is going to give me a pressure of 127.7. And so my new pressure, I'm going to try and bring this over here. My new pressure coming from this division problem is going to be equal to 127.7. And that's going to be expressed in kilopascals. That's my new pressure. Alright, dudes, this is a good example of a really loaded combined gas law problem where all the variables have been changed and altered, and you're still solving for it. So the combined gas law really works well for either altering one or two variables, or even looking at cases where all three variables are being altered. Alright, guys, thanks a lot for tuning in. Hope it was helpful. Have a good day.